Hi, welcome to Proficiency Eagle Series Online. My name is Philip Liang, one of the tutor at Proficiency Education's Eagle class. In order to state rank and come first in the state, getting a raw mark of 100% is sometimes not enough. In this series of videos, I will be posting 4-unit challenge questions weekly, focusing more on how the examiners compare the answers if both students attain full marks. It's recommended that you try these questions yourselves and time yourself before going through the answers. So today we'll be doing a complex vector question. It's a little tricky, and the first part involves us drawing 3 different points, P, P dash, and P dash dash. So the first point, P, is Z minus W, meaning it's the vector from W to Z. But it wants us to draw the point P, so we have to start from the origin. So you can't draw this vector, but you have to shift it to the origin. So in the exam, you would want to use a ruler, so you can measure the distance. So it's accurate, but here I will just freehand it, so it'll be a little inaccurate. So make sure they're all parallel, the length is equal, and so on. The next point, P dash, is the reciprocal. So reciprocal of the magnitude means if we assume the point unit 1 is somewhere inside, that means the magnitude will get smaller. And for the angle, we know that it will get reflected on the x-axis. So again, you want to use your protractors and rulers to make everything very accurate. But I'll just draw something like this. And you can also just write alpha to show that those angles are definitely equal. So P dash. And finally, the last point, 1 over Z minus W divided by cis theta. So this is just the Mars theorem, where you rotate the vector theta degrees, theta clockwise. So you want to measure your theta, and again, making sure everything is very accurate. So you can write theta over here, and the last point is P dash dash. And that's how you do the first question. So moving on to the next part, it wants to prove that if P dash dash is A plus IB, we want to prove that the imaginary part is less than 0, and for the condition that W is left of L1. So one thing we can talk about is your angles, because we know that W is to the left of L1, and if we think about it just visually, the maximum W can be in terms of vertically, it can go up all the way here, and that means the angle of, that means W, the vector WZ, which is Z minus W, it will be pointing downwards like this. So the direction will be this, and the lowest point that W can be is all the way on this line, somewhere on this line, and the angle, the vector WZ will be this way. So we know because W has to be left of L1, therefore the Argand value must be from somewhere here to here. Just thinking about it visually. So we can write this in terms of mathematically using Argand values. So we want to find the angle of this line. So we know it's theta here. So if the direction down here would be negative theta. And if we want to find the angle, so let's write the 0 point. If we want to find the angle of this, well, because these are parallel, we can extend this. That's theta as well. We know that's pi, and therefore that's pi minus theta. So therefore, we can write all of that minus theta. So the Argand value of Z minus W is greater than minus theta, but it's less than pi minus theta. Yeah, so the angle must be from here to here. It cannot be anywhere else. And then we can simply just move through it until we get to P dash dash. So the first one would be to take the negative. And the reason why we can take the negative, why we should take the negative, is because it gives us the reciprocal in the Argand value. Finally, we want to divide it by cis theta. And essentially what that does is taking away cis theta by De Moivre's theorem. So and it's good to write all this out, especially when you're using a theorem. Yeah, so we subtract theta from the angles, and for the Argand values, it will just become what we were given. And like so. So therefore, we're given that the Argand value of P dash dash is between 0 and negative pi. So if we write it in terms of a plus bi, and this represents the imaginary part being negative because it can only be from here to here, and P dash dash imaginary part is therefore b must be less than 0. And that's how you do the second part. So moving on to the last part, we're given this equation, which is this, and we want to show that z cannot lie outside the n-sided polygon. So we're given points z and c1 to cn. c1 to cn are basically just different points of w. I'm just going to draw a random polygon. So labeling the points c1, c2, c3, cn. And we're given that we want to try and prove that z cannot lie outside the polygon. So one way of proving this is using proof by contradiction, where we assume the opposite, meaning that we assume that z does lie outside the polygon. So we want to try and mimic the first part of the question, meaning we want z to be on the right-hand side of all these points of the polygon. And when we're given a point, we can draw any line that does not pass through the polygon. So this whole line is basically L1, and W is basically all these points, and they're all to the left-hand side of this line, L1. So another thing we have to use is this equation we're given. And we realize when we say z minus c1, 1 over z minus c1, it's very similar to the point p dash. But in the point, in the second part, we're talking about p dash dash. So we want to try and convert it using cis negative theta. So if I just times by cis negative theta to both sides, the right hand side still equals to 0, and the left hand side looks very similar to p dash dash. And when we're given this, we want to focus on the imaginary part, because on part 2, we proved that b is less than 0. So that's the part we want to focus on. And we know that if a complex number is equal to 0, therefore the real part is 0 and the imaginary part is 0 if we compare the coefficients. So the imaginary part of this whole thing, which I'll write again, so this must equal to 0 from the property that we're given. But if we use part 2, and then given our assumption that this polygon lies to the left of the line passing through z, the imaginary part of that thing must be less than 0. So if we just take it one at a time, for example, just point C1 first, the imaginary part of cis negative theta z minus C1 must be less than 0, based on part 2. And we can continue this for C2, C3, all the way to Cn. So I'll just write dot, dot, dot. And then if we add them all together, because they're all less than 0, when you take the sum, it's still less than 0. And then you can combine the imaginary parts into just one bracket. And And as you can see, there are clear contradictions between this statement and this statement, because one says equal to 0 and the other says less than 0. So because there is a contradiction, the assumption is wrong, and therefore Z does not lie outside the polygon. So that's almost done, but we're missing one part. So in my proof, I assume that Z must lie to the right of all these points, C1 to Cn, because I wanted to mimic that question so I could use part 2. However, what happens if Z is to the left-hand side of C1 to Cn? Well, luckily the proof is very similar to what we've done before. So everything will be the same, but W will instead be to the right-hand side. And in the end, you can do all of this again. It makes no difference. But in the end, the proof will give you B is greater than 0. And when B is greater than 0, it is still not equal to 0, and it will give you a contradiction yet again. But in this question, because the proof is so similar, it's exactly the same thing, but the sign is changed from less than to greater than. We can simply write similarly. Maybe just before you do the final proof, you can write similarly. If Z lies to the left of C1 to Cn, there is a contradiction. And the contradiction is, again, B would be greater than 0, and from this statement, B would be equal to 0. And that's how you do the last question.